For our final unit, we're going to talk about buffered solutions. Buffered solutions are important, and it's exactly the same as the common ion effect. Nothing changes. Nothing changes procedurally. Common ion effect and buffered solutions are the same thing. So really, this is just walking you through another of the exact same problems. But I wanted to use the word buffered solutions with you because you're going to see this word when you move on into biology. It's one of the most important acid-base solutions. And the most common and maybe most important example is blood. A buffered solution such as blood has the ability to resist a change in pH, meaning our body chemistry stays relatively stable pH-wise, or we'd be in big trouble anytime we consumed anything that was sort of acidic or basic. All buffered solution is a weak acid and its salts, so just like we had before, like hydrofluoric plus sodium fluoride, or a weak base and its salt. And here we have ammonia and ammonium chloride. So we're going to walk through this problem, which is formic acid and sodium formate. Our major species are, just as before, formic acid and the sodium formate. But we don't really need to have the sodium. It's not really part of it. There is only one Ka value, so that's going to be our formic acid. And notice I started combining steps, so we need to make sure that we include some of these other steps again. So we need to write our equilibrium expression because we're going to need that to solve this problem. Okay, we're going to set up our ice chart. And it's ICP. We have 0.250 molar of the formic acid right there. I have 0 hydrogen, and I have 0.1 molar of the sodium formate, which is going to contribute this COOH portion, which is, this is COOH. It's just sort of rearranged depending on which hydrogen you take off. It's the same thing. Minus X, plus X, plus X. 0.250 minus X, X, and 0.100 plus X. Oh, and I did sort of just put that in the wrong spot because it said in that part just to find the initial concentrations, and I went ahead and did the ice chart up there. But that's okay because I need a place to solve it. So I'm starting to combine the steps because at this point these should be pretty rote and pretty easy, and we should just know to do them in that order. So our ice chart should be here. We have our initial concentrations, which we have as the 0.25 and the 0.1, and I'll just use this space here to solve the problem. So then I have X, I have 0.1 plus X, and I have 0.250 minus X. We just circle and cross off. We do that lightly. We don't scribble it all out so that you can't see it. We don't make it so hard that we can't read it. So we're just indicating that we're not using it. And X ends up being 4.50 times 10 to the minus 4th molar. Now we'll get back on track with our steps. We're going to check the 5% rule. So 0.05 of our acid, and we get 1.25 times 10 to the minus 2 molar, which is greater than 4.50 times 10 to the minus 4th molar. So our 5% rule checks. Okay. And then we're going to go on and solve the rest of our problem. pH, H plus, and percent dissociation. So pH is equal to the negative log of our X that we solved for, which is 4.50 times 10 to the minus 4th. The pH ends up being equal to 3.347. Our percent dissociation, we're going to take that acid number, that X we got, we're going to put it over the initial concentration. We're going to multiply it by 100, and we're going to get 0.180%. And So there our whole problem is completed. Now, I know the next problem is for you to practice a basic buffer, but I want to take a second just to set it up for you so that you can get started and know what to do. To buffer a solution at a basic pH, it requires a weak base and its salt. So one might use ammonia and ammonium chloride. Okay, so we're not going to use these chlorides, we're not going to use our alkali metals, we're not going to use our halogens. Our major species are NH3, and we can list it as NH4+. That Cl is not going to be important. We know that the only thing that has a K value or Kb value is NH3. It's going to dominate because it has a Kb value equal to 1.8 times 10 to the minus 5. And our initial concentration of all species involved is we have 0.30 molar NH3 and 0.20 molar NH4+. And I want to write the equation here because this is the hardest part with bases. We know it's a base, but I don't see that OH. Okay, if I don't see that OH, like lithium hydroxide or sodium hydroxide, if I just see that NH3 or something with nitrogen and hydrogen, I know I'm going to have to add water. This is going to steal a hydrogen, so you're going to end up with NH4+. Oh, look, there we go. Now I have a spot to put that, plus OH minus. Remember, this is not going to be a part of your reaction. So getting that reaction is the hardest part. Now you're just going to follow along with the same thing. You'll have initial concentration here and initial concentration here. And remember that you're solving for the hydroxide ion. So eventually you'll have to solve for the hydrogen ion.